Hello, my name is Francis, and I'm here with.
Vanessa?
Joshua Data.
Sebastian Londono.
So we're going to be presenting our CURE project, which is titled "What's in Your Water." For this project, we analyzed a sample of water collected from Proctor Creek, Site 2 in Atlanta. Our goal was to measure two important chemical properties of water: the hardness and the alkalinity of water. These two measurements help us understand how many minerals are dissolved in the water and how well the water can resist changes in pH. Over the next few minutes, we'll walk you through our research questions, the chemistry behind these measurements, the procedures we used, the data we collected, and what our results mean about the quality of the water in this watershed.
The research question being studied is how does water hardness and alkalinity levels vary in tested water samples? And what does these values indicate overall water quality for our tested sample? Our background knowledge is water pollution is the introduction of harmful chemicals, waste, or microorganisms in water. It affects water pollution on humans by causing diseases such as diarrhea and hepatitis. It exposes people to toxic chemicals leading to cancer or organ damage, and it is unsafe as drinking water. So the water quality is an important part of understanding how safe and healthy a water source is. The two major factors help describe water quality as water hardness and alkalinity. The hardness mainly comes from calcium and magnesium, and alkalinity tells us how well the water can resist changes in pH. Studying these values helps us understand the chemical conditions of the water and whether it meets good quality standards.
All right, so to continue with our introduction, which according to the U.S. Geological Survey, hardness plays a role in taste. Our samples came from Proctor Creek, Site 2, which is an urban watershed in Northwest Atlanta. This watershed has been reported by the EPA to have environmental stress from stormwater runoffs, sewage overflows, and pollution. Geologically, Atlanta sits in the Piedmont region, which contains metamorphic rocks like gneiss and schist. These can naturally release minerals like magnesium and calcium into the water. Combined with the urban runoff, these factors can increase hardness and alkalinity. So the location and geology help explain our results. Whereas by analyzing the hardness and alkalinity together, our project gives a clearer picture of the overall quality of the water we tested. So to start off with the procedure, I'm gonna be starting off with the hardness procedure. So for the hardness, we began with the 50 millimeter sample of Water Creek water. We added a buffer to adjust the pH and then added an indicator called Aerochrome black tea, which causes the solution to turn a wine red color when calcium and magnesium ions are present. We titrated the sample using EDTA as EDTA binds to the ions. The solution eventually turns blue. The color change marks the endpoint of the titration. And by recording the volume of EDTA needed to reach the endpoint, we were able to calculate that hardness parts per million. And for our next procedure, which is alkalinity, for that, we again used a 50 millimeter water sample where we inserted a pH probe and added a small amount of molar sulfuric acid. And after each addition, we recorded the pH. During the titration, the carbonate and bicarbonate ions in the water react with the acid. And as the buffering system is neutralized, the pH begins to drop more sharply. Then we continued adding acid until the pH reached around 3.8, which indicates that the bicarbonate ions have been fully converted to carbonic acid, and that sums up the procedure for alkalinity.
So, for our water source information, in our project, we collected our water sample from Proctor Creek Site 2, which is an urban watershed located in northwest Atlanta. And this creek travels through many neighborhoods before it eventually flows into Chattahoochee River, which plays an important role in the city's environment. So, Proctor Creek has different challenges, including stormwater runoff, pollution from urban development, and occasional sewage overflows. And these factors can influence the quality of the water. And according to the EPA, which is the Environmental Protection Agency, the watershed has also experienced issues like flooding, contamination, and aging infrastructure, which affects both the environment and the surrounding communities. By studying the water from this creek, we can get a better understanding of the overall health of an urban water system and how human activity can impact water quality. For the data table, this slide shows the data we collected during the alkalinity titration. Each row represents a measurement taken after adding a specific amount of sulfuric acid titrant to the water sample. We recorded the pH value, the indicator color change, and the total volume of titrant added each time. And the purpose of collecting this data was to observe how the pH gradually decreases as more acid is added. This helps us identify when the sample reaches key points in the titration, especially the endpoints. And all of these values were also used to create our titration curve and to calculate the overall alkalinity of the water sample. For our standard curves, here we have our titration curve that was generated from our data. This curve shows how the pH of the water sample changed as different volumes of sulfuric acid were added. At the start, as we can see, the water had a basic pH around 9. As acid was added, the pH constantly dropped, and the curve shows two major drops. This represents the two equivalence points of the carbonate bicarbonate system. The system equivalence point is where carbonate ions are converted to bicarbonate, and the second equivalence point is where bicarbonate is converted to carbonic acid. Once the pH reaches around 3 to 4, the titration is complete, and the shape and smoothness of the curve confirms that the titration was done correctly. And this curve is what we use to calculate the total alkalinity of the water sample.
So for this section is the calculations that it was performed to technically determine the water hardness using the EDTA titration. And then we compare those results to a strip test. First, of course, we have a non-solution, and then we evaluated the source of errors and the accuracy for it. So for Q1 through A through Z, or D, sorry, technically we did some trials. The first step, of course, it was to calculate the hardness of all of the known solutions using the EDTA titration. The two trials that were performed were trial 1, which used 10.05 milliliters of EDTA, and trial 2 used 10.12 milliliters of EDTA. To find the moles of the EDTA, we needed to use the mole calculation formula, which is N equals M times V, so mole times volume. For trial 1, we technically transformed the 10.05 milliliters into liters, and then we multiplied the known values, which was 0.0010 times 0.01005, which equals to a 1.005 times 10 to the negative 4 power moles. And then for trial 2, same thing, which gave us a calculation of 1.012 times 10 to the negative 4th power of mole. Now, for the ETA, these reactions technically are 1:1 ratio with CaCO3. So technically, both of them have the same mole. For the next calculation, we had to use the water hardness formula. That's the moles of the CaCO3 times the molar mass times 100, and then we divided by the volume, which was the volume in liters. For trial 1, we got 201.18 ppms, and then for trial 2, we got 202.58 ppms. So around the average of the hardness is 201.88 ppm, around there. Technically aligns with the expected value of the known solution. Now, for the accuracy and the source of error, we had to use the relative error calculation formula, which is the calculate value minus the known value, and then we divide that by the known value times 100%. So using the values that we had, technically we had to do 202 minus 200 divided by 200 times 100%, which gave us a percentage of 1. So technically a relative error of 1% indicates a high accuracy. Some of the potential sources of error could have been like, errors when reading the burettes, inconsistent mixing, incomplete reactions, and finding out the endpoints being erroneous or just miscalculating it. For the Creek sample, technically we use 46.20 millimeters of the EDTA solution. And of course we had to switch it to liters. And then we had to do the same thing, find the molarity by calculating it, which gave us a 4.62 times 10 to the negative 5 moles. Then same scenario, the ETA with the calcium carbonate, if I'm not mistaken, which is CaCO3. It's a 1:1 ratio, which technically has the same mole. Then we did the ppm test with the formula, which gave us a 92.48 ppm. And then technically for the strip test comparison, it measured 120 ppms, and the titration calculated 92.48 ppms. So the difference is, you could say, is around like a 20 to 25%. That it shows that the strip test was technically overstimulated hardness. Is kind of expected when it comes to the strip test, because it provides like a approximate result. So that's where the titration is like a little bit more precise. And then for our conclusion, the titration results indicate a hardness of about 92 ppm, which I mentioned, compared to 120 ppms from the strip test. The clear equivalence points in the titration curve confirms the reliability of the results. Moderately, hard water contains dissolved minerals, which is normal when it comes to a natural resource or source, and it's not harmful. And of course, these findings help provide insight into the water quality and answer research questions.
And these are going to be our sources, which are scientific and government sources we use for the background information of water hardness, alkalinity, and then the Proctor watershed. And this all helped in the findings of what we had for the project. Thank you very much.